histogram gets us the shape. So, you got your machines. Let's graph our data, and let's also see where all of this stuff ties in. Where all this stuff ties in. Okay, to graph a histogram on this bad boy, I'm glad we're recording this, because we're going to be doing this pretty much all the time in here, and definitely all the time at 244. You got to get to your stat plot menu. You might see it up here above your y equals button. It's either yellow or it's blue, depending on what model you have. So second, y equals. Okay, here we are. There's your plotter. You got 3 plots you can turn on at one time. We're eventually going to be graphing 2 things at a time, a box plot and a histogram. But for right now, just a histogram. First thing you do, let's grab plot number 1. Oops, hit the wrong damn button. Sorry. Second y equals plot number 1. There we go. Now you got some choices here. I'm guessing your screen looks pretty much like this. First of all, turn it on by pressing enter. Now press down. And now you've got a choice of 6 different plots. 2 box plots, which are fantastic. A normal quantile plot, which is equally fantastic. We'll play with that in 244. Scatter plots, totally bitchin'. Play with that in 244. A line plot, they're okay. They suck on a TI, so I very rarely use them in here. And this guy right here, there's your histogram. Right arrow over to that one, and then press enter, and now you got your histogram fired up. Now you may have noticed as soon as you press that histogram enter, this down here changed. It went from X-list, Y-list, mark to just X-list and frequency. That's good, because this is single variable data. Scatter plots are double variable data, bivariate data. Is your data in L1?
Yes.
It is. This frequency, this just asks how many times should we count our data. And when you have raw data, it's always 1, because it means count every data point 1 time. That's when you have raw data, just leave it just like that. We'll deal with group data momentarily. I'll show you when you don't want to deal with a frequency of 1. When you are happy, oh, there's one more thing we're going to do one time. One more thing we're going to do one time. Press the y equals button just by itself. Do you guys have any equations turned on?
Yes.
Get them all out of there. Just hit clear on all those things. They just get in the way. They get in the way. I mean, they don't actually affect anything except they look bad when you got like parabolas coming across this direction. Or maybe it looks nice, I don't know. But just make sure it's clear. We're not going to use that screen at all in this class. I know you use it a lot in 111 and tons in 95, but there's no point for us in here. Getting away from equations, getting more towards big concepts. Okay? Now you're done. So I want to see my graph. The easiest way to get a quick graph is to press the zoom button, which is your preset zooms. And there's one, number 9 is called zoom stat. You can look for it down there if you want. What this does is it picks the window on your TI that best represents what it thinks best represents your data. So go ahead and press 9 or enter. And there we go. We should all have roughly the same graph. Roughly the same graph. Fair enough? Now, whenever you press zoom stat, the following happens. It picks your smallest data set, the smallest data point, and puts that at the far left. It picks a largest data value, and I don't know how. It's something the magic of the brain. And then it divides the range into 7 equal regions. So you've got 1, 2, 3, 4, 5, 6, 7, one of which is blank right now. One of the first things I like to do is I hit the trace button and I see exactly what numbers it's broken it into. So if I hit the trace button, you see how it says min is negative 58, max is less than negative 44.83333. That means it's counting the number of data points that are bigger than that, but less than this. So bigger than negative 58, but less than negative 44. That was that one negative 58 that was in there. And it's telling me there's one of them. There's one of them. I hate the fact that it calls it N. I wish it called it F. N is the entire sample size, but it's TI. They ignore my email. Scooch over 1. This will tell you. Scooch over 1. It's now telling you there are 3 data points that are at least negative 44.83, but no bigger than negative 31.7. And if you look in your data, you'll find that too. Okay? And that's great. It'll do that for every single data point. They're all accounted for in there. I'm a tinkerer, though. These numbers give me a headache. There's too many decimals floating off the end. It's hard for me to subdivide it in my head. The first thing I'll usually do is go in and adjust that myself. So here's what I like to do, and you don't have to do this. I just like to do this. I press the window button, and I change at least these three numbers up here so they're quote-unquote nice. See that negative 58? I hate it. Make it negative 60. Just make it an easy number to do math in your head with. This is why. This is why. See that 34? Our biggest data value, I think, was 21. I think, right? You can make the 34 either a 30 or a 40. Your guys pick. What would you like to go? 30? Let's make it 30. So go down, change this to just 30. Whew. And if I make that 30 and I drop down, this is the most important one for me anyway. The X scale is how wide each bar is. Remember it was saying negative 58 to like 45.83333. That's how, let's do what? That's what I'm saying, Kate. Let's do 10. Give it a nice logical value like 10. Because that's easy to visualize in your head. I can't visualize 13 2/3, whatever the hell it was a minute ago. Now, if you choose to finagle, and I encourage finagling with this, press graph now. Don't press that zoom 9 again. The zoom 9 you're only going to press one time. When you first enter the data and press zoom 9, you get a histogram. It gets you in the ballpark. This is the refine. When you press the refining graph, aha! There it is. Now, does it look similar to the last graph? In what way does it look similar? Good, hold that thought, Jenny. In what way does it look similar? Andrew, nice and loud, please.
Bell shape.
It's basically a bell shape. The last one, remember what the last one looked like? It had a little tail here, and then it crept up, and then it kind of tailed off. I think it was a little bit bigger on this side. But this one is too. You got a little bit of a spike here, but it's bigger over here a little bit. So, but it's essentially a bell shape. We're going to find out ways to measure bellishness or non-bellishness as we go through this course. But it's essentially a bell shape. Good. How does it look different? Jay, is that what you were talking about? Okay, it looks the same. Go ahead. How does it look different?
There's more outliers, or
There's
bigger on the side?
There appear to be more separate pieces out here on the side. That's a function of the... Good. Thank you for that. Watch this, friends. If you go back to your window button, remember that scale that Kate said, use 10? Change it to 5. Change it. Good for you. We encourage finagling graphs graphically in here. Change it to 5, regraph. And you see what's happening? The more you refine it down, the more of these little holes you're going to start seeing, because the data that's fairly spread out is going to be indicated with more holes. It's still the same distance. It's still negative 60 out to positive 30. But now you're refining it down so much. You can essentially get it very close to a dot plot if you refine it down far enough. If you make them all one wide, you'll eventually get a dot. I mean, I don't think you can do it. I think it gives you an error if you try. But you can get it pretty close. You can make it down to 2. And if you hit graph now, you see? But it still, Andrew, looks kind of... It still looks kind of bellish. It starts in a tail, rises up, and then tails off again. You have to think outside the algebra box. It's not a perfect bell. It's not a perfect bell. But it's a small sample. You have to allow for sampling variability. So if you look at it, here's what I tend to look at. I'm going to go back out to a window with a scale of 10. Okay, I'm just going to leave it like that. Because it's bellish, but it's also kind of goofy because it has the 2 spikes on it. When you're trying to decide whether or not a graph is bell enough, this is just a gut for right now. We'll have measurements for it soon enough. Look for the 2 sides being tailed. Okay? Look for them going down to tails. If you can check that off, that's a good start. Then, kind of come in a little bit. If you can roughly imagine a bell sitting on top of that thing, you're going to have some that are out, some that are under, some that are over. But if roughly it's sitting where the bell should be, then yeah, you can say, I think it's bell enough. We'll have formal measures for it, I promise you. I promise you. But for right now, I agree, I concur, that's bell-shaped enough. Bell-shaped enough. Now, why I keep saying bell-shaped? Well, Andrew said it first. I shouldn't take credit for it. Andrew's going to say it first. But here is what I'm talking about. When you have bell-shaped data, you can assign percentages to these standard deviations. That's what's totally freaking cool. Can you see the average on this curve? Where is the average on this curve? Where is it? Where's the average on this curve? Well, where is the average of our data set? It's negative 15. Can you see negative 15 on this curve? Well, what's nice about this is we picked very nice numbers. This is negative 60, right, down here. This is negative 50, negative 40, 30, 20, 10, there's 0. This is 30, right? Where's negative 15? Right there, huh? There's X bar, between negative 10 and negative 20. There's your average, there's your balance point. Now you can see why that balances. Yeah, we got a little bit of weight over here, but that's being countered by that little bit of weight over here. And it's averaging out to negative 15. It goes back to JC's idea of the whole spreading of the data. Can you see one standard deviation from negative 31 to 1? Go ahead, JC.
This might be moving along.
That's okay, go ahead, move along.
So when you go to do the window on the X scale,
Yeah.
I know where we're headed. So when we do the bell and then you chunk with the standard deviations, is it better for it
There's no quick and easy, I see where you're asking, there's no quick and easy answer for that because these numbers just agree, well actually they don't, watch this. One standard deviation is negative 31 to 1. Negative 31 doesn't show up evenly on this. I mean here's negative 30, so negative 31 would kind of start here. And 1 would be kind of over here. So that's one standard deviation right there. Okay? So really, I mean, the problem with trying to get too exact on the scaling is you're probably never going to be able to get everything laying exactly on a scale mark. Is that fair? There's no good answer. And that's the idea. You're not trying to really, you're just trying to get a ballpark estimate of what the thing looks like. It looks like a bell curve. Cool?
Yeah.
Now, I drew two lines up like this. Hattie, a few moments ago, i.e. 30 minutes ago, you said that most of your data should lie within that first standard deviation. And of course, wise ass me said, assuming, what was I talking about? Assuming that your data is bell-shaped. What percentage of our data led? What percentage of our data? Did we get exactly 68? What's 24 out of 35? We got 24 data points. That is the majority, correct? As a percentage, what's 24 out of 35? 69%. Scholar said 68%. There's a uniform rule, it's called the Empirical Rule. The Empirical Rule, I think your textbook calls it that, a lot of textbooks do. If you have bell-shaped data, roughly 68% are going to lie within there. I'm not a huge fan of 68%, I like to call it 2/3. About 2 out of every 3 data points lie within one standard deviation. Because 2/3 is nice, if you can think about that. 2 out of every 3 data points. One's out, 2 are in. One's out, 2 are in. Fair enough? That's the first standard deviation marker. 68% or 2/3 of your data-ish. Good so far? That's one standard deviation. We'll call that blue. We'll color coordinate it over here with the A. 2 standard deviations, the ones I put the orange star around. Make that orange, why not? Now clearly, it's still centered on the average, which is right here. But it goes down to negative 47, which is like out to here. And it goes up to positive 17, which is about out to here. Now you'll notice, if you sketch lines up, 2 standard deviations completely contains 1, and it also picks up more. What percentage of our data is in there? 33 out of 35, something like 93, 94, somewhere in there? I'm going to make an Excel video to show that the theoretical percentage is 95.44%. I'm going to show you why using Excel. I'll get you a YouTube video for it. Don't memorize that. Don't memorize that. The one you want to kind of keep in your head for the empirical rule is 95%. Basically, 19 out of every 20 data points are going to be within 2 standard deviations. 1 in 20 is going to escape either high or low. 1 in 20 is going to escape either high or low. 1 in 40 up and 1 in 40 down, which comes to be 1 in 20 altogether. What do we call those that escape high and low? Those are the ones we call outliers. So we do have some outlier data in this. That negative 58 and that positive 21 are too high and too low. See the quotes? See the quotes? Too high and too low because we have made them be such too high and too low. Does that make sense? It's all definitions at this point. As far as 3 standard deviations, we'll go with red. That goes out, and we're actually off our graph now. Negative 63 way down here, all the way up to 33 up here. All the data's in there. I got news for you though. The empirical rule doesn't say all the data's in 3 standard deviations because sometimes it's not. It happens to be in this. Most of the data is, almost all of it is, and it rounds to 100%. It's more like, I think it's 99.5 or 99.6 or something like that %. In other words, a few per 1,000 escape. So what we said, within 1 standard deviation, 2 out of every 3 are within 1. Within 2, 19 out of every 20 are within 2. When you get out to 3, it's something like 997 out of every 1,000. So it gets really freaking hard to get outside of that. You have to be one of those 3 in 1,000. And every time you go out further, you pick up a higher percentage, but you never pick up 100%. You go out as far as you want. Bell curves theoretically tail off to infinity, and you never actually pick up 100% of the data. Has anybody ever heard of 6 Sigma? It's something corporations used about 10 years ago. I think they're still using it now, 6 Sigma. Well, I'll say a bit about it, not very much if you haven't heard of it. Companies that make lots and lots of things, like computer processors or little tiny wires that go inside of computer processor parts, or any manufacturing that generates hundreds, if not thousands upon parts, realize that if we catch 997 out of 1,000, we're missing 3 in 1,000. Well, if we're making hundreds of thousands of parts, we are now allowing too much variation, because you multiply 3 in 1,000 out by 1,000,000, and all of a sudden you're like, holy crap, we're off by 30,000. So they said, 3 isn't far enough. We've got to go out 6. And they called it 6 Sigma, I think because 6S probably didn't sound cool enough. They used Sigma, which is that little tiny Sigma. Remember that little guy, the population? They called it 6 Sigma, and they said, we're going to shoot for 6 Sigma. 3 Sigma's not big enough anymore. We need 6 Sigma. And the reason is, when you get to 6 Sigma, you've trapped like 99.9999996%, which means you're only missing 4 out of every like 10 million. That, they term that as acceptable. Because those customers, you just send them a free one, and you haven't lost a lot of money. But if you're losing 3 out of every 1,000, and these things cost a small fortune, then you're hemorrhaging money, so you have to shoot for a better tolerance. Hemorrhage, I love the word hemorrhage when it comes to money. It's just hemorrhaging money. Cool-ish, fair? So Hattie, I love what you're saying, and what's cool about this is we can revisit Scott's percentages. So I go back to my original question, is the weight loss program working? Yes, on average. But can we be even more specific now based on this idea of standard deviations? I think so. I can say 2/3 of the people that use it are going to lose no weight, but maybe as much as 31 pounds. You see what I'm getting at? That's kind of slick. Now we can not just say on average it's negative 15. Even Scotty, I love what you said, most lost weight. Yes, but we can also quantify it too with the percentage, huh? Makes sense? Yeah, it gives us one more refined tool. All the tools you guys are saying are awesome, and they're all correct. This just allows us to refine it even more. Refine it even more. Now you can see also, if you go too far out, it becomes meaningless. Does the weight loss program work? 100% of our sample subjects lost between negative 58 pounds, and some of them gained 21. I'm not trying to advertise that. I'm not trying to advertise that, right? But to be able to say that 2 and 3 gained no weight and maybe lost as much as 31, that's not only correct, but it's persuasive. And that's cool. That's cool. It's not misleading in any way. It's not misleading in any way, and it's persuasive. That's like good statistics, and good marketing for that matter. Not that statistics has to be about marketing, but it's actually proper use, as opposed to the freaking weight loss programs that put the outlier up there. This 51-year-old grandmother of 4 lost 62 pounds, and at the bottom in 12-point font they're saying, you know, results may vary, not everyone loses weight, results not typical. So basically what they're doing is they're showing you her and saying that's how we're going to sell our product, ignoring this. And that pisses me off. Jared from Subway, we'll talk a lot about him. Yeah, Kate.
So how are you guys doing, 1S or 2S? Wouldn't it be better marketing if you did like 1.5, where you don't have the plus 1 pound, you're only looking at, well...
Careful. Careful.
Isn't that better marketing?
That's controlling the statistics to make it look a certain way.
I'm just saying it's-
Better marketing for me would be to go sample more people and shrink that bad boy down even more. That would, I wouldn't say it's better marketing, I say it's probably the kind of marketing they would do.
Okay, that's what I'm saying.
But ethically, I think it's questionable. I mean, ethically, 1, 2, and 3 standard deviations are so prevalent in, not many people understand statistics. Those that do understand 1, 2, and 3 standard deviations. Skylar, you popped out 68% as soon as I mentioned 1 standard deviation. To mess with that is to mess with kind of the underlying culture of a standard deviation that is not known by many people anyway. So when we start kind of caressing it to make it not include the 1, I think we're getting into ethical territory. It's my opinion. That's my opinion. It's not that.
If they were gonna do it, that's.
You couldn't do it. Shrink the standard deviation down a little bit, 0.9. 0.9 standard deviation. What the hell's a 0.9 of a standard deviation? Then it becomes a math problem. And I try to avoid that whenever I can. But it's a good point, Kate. You totally can control it that way, and you'd still be honest. I mean, you're reporting true statistics. It's just that they're starting to pull, I think, in a way that's getting a little bit unethical. Just my opinion. Just my opinion. Gray. Totally gray. Cool? So now, you know what to do with bell-shaped data when you have it. You can go one step further. You can give me the average. You can give me the standard deviation, and you report on percentages. It's freaking fantastic. But what if you don't have the raw data? I collected some more data for you guys down here. I have to update this. This is from 2009. Portland Marathon. Let's restart. We're stopping again.